traffic analysis in wireless networks, and I just want to recap. We had an overview of traffic models and service systems. Using the basic theory of service systems, we have derived two models. The first one is very simple and well known, which is the Erlang-B model for a limited number of resources and no queue in the service system, which is also known as pure loss model. Then we have extended that model to the case of multiple services that require multiple rates, capacity, portions, and we have generalized the Erlang-B with the extended Erlang-B formula, which is basically a version of the formula which, thanks to the symmetry property of the Markov chain, which is associated to the formula, we have a formula which is just a kind of multi-dimensional version of the Erlang-B with the same structure, and that's the reason is that the solution of the equations for the stationary probability is based on symmetry properties of the chain. I didn't mention that even if we have arrived the formulas using Markov chains, it is possible to prove both for the Erlang-B and the extended Erlang-B formula that the formula for the loss probability holds also in case you don't have exponential distributed service time. So these kind of properties of the system are valid under general assumptions on the distribution of service times. So it can be an arbitrary one, not necessarily an exponential distributed service time, like in the case, in the assumption that we need to have for the Markov chain. Even if you have an arbitrary distribution, constant service time or whatever distribution you want, the Erlang-B formula and the extended Erlang-B formula, they still hold. Okay, so they are valid under general assumptions on the service time. Of course, we cannot relax other assumptions, and of course, if you don't have Poisson arrivals, then of course everything changes, and of course, the analysis that must be done in terms of the accessibility of service is rather different. Okay, I don't have the time, but there are models that are able to characterize different types of arrivals. For example, to model one of the phenomenon that is known in the behavior of users that access a communication service, which is the retrial behavior, right? If you find the system busy, typically you retry after a while to access the system. This creates a correlation in the arrival process, which of course is not in line with the assumptions of a Poisson process, and can be modeled in a different way in order to characterize the behavior of systems in the case of these retrials, right? In particular, when you have congestion conditions, this is something the operators tend to do, right? It's complicated, right? So they do it based on the assumptions and the information they have. But if you have a big event in an area, temporary event in the area, and you expect some congestion in your network, of course, while you get close to the congestion point, this effect of retrials can be extremely negative in terms of the service accessibility. So you can worsen the situation because of these, correlated attacks. Okay, but anyhow, let's focus now on something else. before moving to models that can be used for mobile networks where you have mobility, so which means that you don't have just one single pool of resources that can be accessed, but you have different pools that are somehow distributed over the territory based on the spectrum assigned to cells in the area. Let's first make a step back and consider one scenario which apparently is not suitable for an analysis like the one that we just did, which is CDMA. CDMA is a technology for multiple access and multiplexing in mobile radio networks that is used in UMTS, third generation systems, that we will study later on. And we know that CDMA is different from the other techniques for multiple access, mainly because we don't have orthogonal channels, we don't have orthogonal signals. So we have cross interference between channels assigned to different traffic flows, poles in the same cell. Is this something that will affect the use of a traffic theory like the one that we have studied for the case of orthogonal signals, or can we extend it in order to include also the case of CDMA, right? So in order to understand why CDMA is different, we need to make some little steps in the direction of analyzing the capacity of a CDMA cell. Because if I ask you, I hope, if I ask you what is the capacity of a TDMA cell, which has a number of time slots per frame, and we know, for example, that one time slot per frame is exactly the capacity that we need for our service, for example, telephone calls, right? Then for you, it should be very easy to say, okay, what is the capacity of that cell? What is the capacity of a cell with n time slots per frame? Capacity, we need to define capacity, right? I hope this is intuitive, it should be something that you already know, but capacity can be the capacity of the channel in bit per second, or can be the maximum traffic that can be sustained by the system, right? So if we consider voice calls, then the capacity is the maximum number of simultaneous calls that you can serve in the system, right? If you have n time slots and you assume that the capacity of one time slot per frame is exactly the capacity of a telephone call, so a coded voice signal, then simply you can have up to n, right, simultaneous calls, right, per carrier. We will see that in TDMA typically you have multiple carriers, and you have TDMA on each carrier, so you have frequency division first, and then on each spectrum portion that you obtain with frequency division, then on each one you have a TDMA, right? So you have n time slot per carrier. So if you have C carriers and n time slot per carrier, you have maximum C times n simultaneous calls that in your system. And this is fixed, right? It's easy to see that signals are orthogonal, they don't generate mutual interference, so that's the capacity. That's the maximum traffic that you can have in your system. What about CDMA? CDMA is different because you generate mutual interference, because codes that we use for this purpose are not orthogonal, right? So can we characterize the capacity of CDMA? And the definition is the same: maximum number of simultaneous conversations, voice calls, data connections, whatever, right? That's the point, okay? So this is our goal now. Okay, so this is what I just said, right? So I will not mention anymore. So in CDMA, we have channels that share the same band, right? So they are spread over the same spectrum portion. There is no mechanism for separating them. We will come back to the concept of reuse. And therefore, the problem that we have is in calculating the capacity is the usual problem that we have in any communication system. In order to ensure that each one of these traffic flows, voice calls, for example, has a good quality, we need to guarantee that at the receiver, the signal-to-noise ratio is above a threshold, right? That's the usual way we use for dimensioning a communication system, right? The only point here is that at the denominator, we don't only have noise, but we also have interference. Somehow, interference is one of the components of noise, which we cannot ignore, and typically this is actually the dominant component of noise that we have to use in order to characterize the system and dimension it, right? So that's why typically we use signal to interference ratio. Should be signal to interference and noise ratio, right? Because at the denominator you have interference and noise. Okay? Clear? So, so in the end, right, we know that if we, and again, this is from the basic courses of transmission systems, what we use for characterizing the quality is the error probability, right, bit error rate. And the bit error rate, depending on the modulation scheme that you use and the coding scheme that you use, is basically in the end a curve which is the error probability versus the signal to interference and noise ratio, right? Well, actually, what we use is the energy per bit divided by the spectrum density of the interference and noise, right? So it's AB over N0, right? And you know that's the starting point of any analysis of a transmission system, right? So somehow, if you consider a quality parameter, typically what you do is that you set a threshold on the maximum tolerable bit error rate, and using the specific modulation and coding scheme that you have, then you can calculate the maximum value, a minimum value for the AB over N0, which is the minimum one over which you can guarantee that the bit error rate is below the quality threshold that you have set, right? Very simple, right? So depending on the modulation scheme that you have and the coding scheme that you have curves like this one that can be used in order to characterize the behavior of the system, right? Very good. Now, so in the end, you have a B over N0, which is your parameter that make you move up and down in the quality level depending on the propagation conditions, both for signal and also interference, right? So how can we rewrite a B over N0 in a way which is more suitable for us to understand what's the impact of on CDMA systems of this basic structure of any transmission system. So actually, when we say energy per bit, what we have is we can rewrite it as the signal power divided by the bit error rate, right? The bit rate, sorry, the information bit rate. So if you divide S by the rate in bit per second, what you get is the energy per bit. And that's a different way of characterizing the energy per bit, right? Note that RB, the rate, is the information rate. So the energy that you assign to a bit is a bit of information, right? And this is, of course, something that is independent from the way you then collect the energy at the receiver. So this is the energy at the receiver. The way you put together this energy does not impact this parameter, which is the one that we use for characterizing the bit error rate of our modulation encoding scheme, right? And the spectral density of noise is, of course, something that assumes that the noise is uniform in the spectrum, right? However, if you want to, you can write it as the noise power in the bandwidth of the signal, right? So if you consider a specific bandwidth B, which is characterizing the signal, of course you don't use a bandwidth for characterizing the noise, but we can consider the bandwidth of our signal, and then the energy of the noise in this bandwidth is the one, the power of the noise in this bandwidth is the one that, of course, impacts our transmission scheme. So N0, the spectral density of noise, by definition, can be written as the power of noise in the bandwidth of the signal divided the bandwidth. Okay, that's very easy, right? So if we replace in the formula of FB over N0 these two different ways of writing AB and N0, what we get is something that can help us in better understanding the behavior of CDMA systems, right? So we simply replace in the formula these values, and what we have is that we can rewrite things in such a way that we can observe that a B over N0 is actually something that can be written as S over N. S is a signal power and N is the noise power. And since noise power is in the bandwidth of our signal, you also understand that N can include interference in the end. That's the reason why we go this way. And then times B over RB, the bandwidth divided by the bit rate. Okay? So the bandwidth divided by the bit rate is something that, of course, is a parameter that we call processing gain, and it's something that characterizes any modulation encoding scheme. However, we are particularly interested in characterizing this parameter GP, processing gain, because in the case of CDMA, we use this specific parameter in order to make our system able to, at the receiver, separate the signals and reobtain the signals transmitted over the different subchannels with different code rates. Why? Well, the main point is that with CDMA, what we do is really making GP very big. Why? I said to you that RB is the information bit rate. So it's the bit rate of each channel that we multiplex together with the others in our CDMA system. So it's the bit rate of each component of the multiplex signal. If we multiply each symbol, each bit of this information flow by a code, what we get is something that, of course, has a larger bandwidth, right? So somehow, we keep constant RB and we enlarge B. That's why we call it spread spectrum, right? So the process of multiplying each symbol by code, that is the fundamental characteristic of CDMA, has the effect of increasing remarkably GP. Clear? Clear for everybody? We also know that we obtain a similar effect also with channel coding. For example, if you use a code rate of 1/3, right, it means that you transmit 3 bits and per one information bit. right? So similarly, also with for error correction, channel coding, we increase this ratio, we increase the processing gain. So two are the main components that make GP big, that can increase GP in CDMA system. One is the code, spreading code, what we call the spreading code, the one that we use for multiplying each individual symbol of the different channels, sub-channels, and channel coding. By far, the spreading process, this multiplication by code, is the main one that make GP big. And the reason is that typically the codes that we use are very long, right? Up to hundreds of bits or chips per bit, which means that the spreading effect is the dominant one in CDMA systems. This is of course not true in other systems, for which of course you can do the same analysis, right? But CDMA systems are characterized by this, huge value of GP, typical big value, huge value of GP, which is due to the spreading process, right? So therefore, GP is much bigger than 1, right? And if you assume that the system for the rest is characterized by a spectral efficiency which is in the order of 1 bit per hertz, which is not far from reality of these systems, then you can also somehow say that if you want, the GP is well approximated by simply the spreading factor, which is the number of chips per bit, right? So the number of chips in the code. Clear for everybody? So that then, can we also somehow explain this behavior in a way that is intuitive, like we did before when we try to characterize the basic principles of CDMA? Well, in the end, you can see that the formula that gives you a B over 0 as function of the signal to noise and interference ratio multiplied by GP is actually just telling you that at the receiver, when you decode your signal, you make the signal that you are decoding narrowband again, while you keep the other spread over the bandwidth B, right? And the ratio between this bandwidth and this bandwidth is exactly the spreading factor, right? So if you, instead of filtering the whole bandwidth, at the receiver, if you filter only this bandwidth, you reject all the energy or the power of the interfering signals that is outside this bandwidth. This rejection of this filtering out of this noise power is a gain. And you understand that the gain is exactly the ratio between this bandwidth and this one, which is exactly the spreading factor, right? So this is, the intuitive way of understanding why you have this, factor multiplying the signal to noise interference and noise ratio, which is somehow the gain of the system. And the gain of the system is the one that you obtain because you are bringing back your signal to the original bandwidth and rejecting the interference which is outside. So this is another way of understanding why. Now, clear? Well, now, okay, can we use this for calculating the capacity of a cell based on CDMA? How many simultaneous channels can we have? How many simultaneous voice calls, for example, can we have? Right? Well, somehow the point is that we need to calculate the AB over N0 for each of the signals that must be received. So let's consider, for example, the case of the uplink, right? Of course, then I will come back to this. But for the moment, let's assume that we have terminals transmitting at the base station and the base station receiving. For each one of these signals that the base station is receiving, all of them are overlapped in the same bandwidth B, and the base station is in charge of decoding each of them. Okay? For each one, for example, high, we need to characterize the quality of the decoding process, right? So we need to calculate a B over N0 for this specific signal I. How can we do that? Well, we can use the formula and we can calculate the signal to interference and noise ratio times GP. GP, of course, is a constant which is characterizing the specific system that we have. So let's use it directly, and of course the value depends on the system that we have, right? Now, at the numerator, what we have is the received signal power. The received signal power somehow is proportional to the transmitted signal power that we can indicate as Pi. So Pi is the transmitted signal power multiplied by a constant which is somehow putting together the path loss and the antenna gains, right? So Gi is the channel gain, which is typically less than 1, so actually it's an attenuation, of course, right? But somehow it's the proportionality constant that link you the received power with the transmitted power, right? So it's a combination of the channel characterization and antenna characterization, Gi, okay? So we transmit Pi, we get Gi Pi. Well, we get Gi Pi for our specific signal I that we want to decode, but we are at the base station, we are receiving also the others, but the others now are interference, right? Because we want to decode exactly signal I. So all the others, which have, of course, the same structure, so GK, PK, with K different from high, so these are the other sub-channels that are multiplexed together in the same bandwidth B, right? So we want to decode one, but we receive all of them. So the one that we want to decode is our signal, the others are interference. So they go to the denominator, plus noise, right? Times GP. That's very easy, and that's the value of AB over N0 that we want to calculate. Of course, we know that in order to calculate the capacity of our signals, our system, we need to guarantee that AB over N0 is greater than a threshold, which is our quality threshold. So in the end, the capacity is obtained just assuming that this value must be greater than a value, than a threshold. Okay? Clear for everybody? Very well. Now, okay. How many signals can we put together, right? Well, you can easily understand that if you start adding new components to the system, new signals that are multiplexed together, basically you make the denominator bigger, right? Because you increase the number of signals that are considered interference at the denominator. You start from 1, 2, 3, 4, you start adding new signals, but what you are basically changing in your formula there is the denominator. You are making the denominator bigger because you are putting more signals in the same bandwidth, right? So it's pretty intuitive that if we have a constraint on the minimum signal, the minimum AB over N0, you cannot keep on adding new signals because at a given point you will not be able to guarantee that AB over N0 is greater than the threshold, right? See? Okay? So somehow it's clear that this equation can give you the capacity, right? Very good. Now, the other, and that's okay, very obvious. The other point, which is a little bit less obvious, is the following, right? This condition, a b over n0 greater than the threshold, must be guaranteed for all signals, not only for I, but for all of them, right? If instead of taking I, you take J, another one. So basically, you just take one of the elements of the denominator and put it at the numerator and bring the other one down, right? So all the conditions have exactly the same structure, exactly the same components, right? You just move one up and the others down, right? If you need to ensure that all of them are satisfied, in the end, you will have a 1, which is the dominant one, right? That will limit your capacity. So if you have GI, PI all different, which is the one that will limit your capacity?
The one with the small.
The one with the GI, PI, which is the smallest one, right? Of course, right? So it makes no sense somehow to have the values of GI, PI all different. So if you have the possibility to adjust powers, right? The only reasonable way of adjusting powers is in a way that they, at the receiver, they are all equal. Because if they are all equal, all these equations that we have there are equivalent. So it's kind of just having one single one, which is your capacity equation, right? So that's the reason why in CDMA system, power control is extremely important. Power control is a technique that is used for characterizing, adjusting powers to the transmitters in a way which is convenient for decoding at the receiver. In the case of CDMA, what you do is that you adjust powers in a way that will make GI, PI equal for all subchannels at the receiver. To be more precise, in these systems, you typically have two approaches. One is known as open loop, and the other one is known as closed loop on power control. In the case of open loop power control, you guarantee that GI, PI is equal to a constant. GI, PI is equal to a constant. Why? So GI, PI equal to a constant. Okay? Why open loop? How can you adjust in practice? How can you adjust the power in a way that you will be able to compensate the losses during transmission, so the channel characterization, such that the receiver power is equal to a constant for all signals? How can you do that? You need to, yes, you need to characterize the channel. You need to know GI, right? If you don't know GI, you cannot compensate. How can you know GI? That's the point.
Channel estimate.
Okay, how can you estimate channel? Simple way. Signaling, okay, how?
Besides the apparent symbol of receiver and transmitter.
That's true. Okay. So, okay, I see that you studied something at physical layer, so you know what is a pilot signal. However, in that case, pilot signals are typically used for characterizing the transfer function of the channel, not the general attenuation that you want to use for power control, right? So the simplest way of characterizing the attenuation of the channel is transmitting a reference signal in the downlink, assuming that the channel is symmetrical. If you measure the received power on the beacon transmissions of the base station, the broadcast transmission of the base stations, then you can characterize the attenuation also in the reverse direction, right? So it's called open loop because you just listen to the broadcast transmissions that are at constant power, constant and known power, and since the power is known, you just measure the received power by from the base station, and just comparing the value of the transmitted power that is known and the received power, you can estimate GI in the uplink, right? So you can compensate autonomously at the terminal the power simply because you can measure the received power from the broadcast transmission beaconing of the base station. That's open loop, right? In the case of closed loop, things are a little bit different. In the case of closed loop, the point is that you make estimations at the receiver and you send to the transmitter commands for increasing or decreasing the power. Okay? So that's the difference. So I'm not making the power adjustment autonomously, open loop, but I'm estimating something at the receiver, and then the receiver is sending back a signal to the transmitter in order to increase or decrease the transmitted power. And it's really closed loop, which means that you have this continuous measurement, feedback, and so on. Exactly like in the case of the timing advance for TDMA. If you move up and down in the cell, you increase or decrease your propagation delay, then the mechanism is closed loop because you keep on measuring in order to make adjustment of the time alignment. Similarly, you continuously make measurements and then make adjustments with commands up and down in order to keep the value. Which value in this case? So since you are doing an estimation at the receiver, you can estimate something more than just the received power. You can estimate the signal to interference and noise ratio, right? In that case, you need your pilot symbols in the transmitter in order to identify estimate the power of the signal and separate it from the power of interference. Then that's one of the fundamental processes that you do in channel estimation, right? So you can do that only at the receiver, but then it's the transmitter which is in charge of setting the power, so you need to tell to the transmitter if the power is too much or too low and make the adjustment. Very well. If we consider a given cell in the uplink with just interference coming from the transmissions in the same cell, like in the example that I did before for the formula, then these two are equivalent. These two approaches are equivalent because in the end, the only components that make your signal to interference ratio different from others is the constant component, in particular the noise power. So in the end, the final effect is the same. In case you have multiple cells generating interference in each other, then things are not so obvious, and of course you have a difference in the approach. The one that we use in CDMA systems, like third generation system, is the second one, closed loop power control. Okay? But for the moment, we don't make a distinction between the two. We just assume that the GI/PI is constant, right? So if GI/PI is constant, equal to PR, which is received power, right? So the received power from each individual subchannel is a constant. We can replace in the in our formula GIPI for all I with PR, and what you get is exactly what is written here. So of course, n in this case is the number of signals that are multiplexed together in the same bandwidth. N minus 1, why n minus 1? Because you have 1 at the numerator and n minus 1 at the denominator. Okay? And that's the value which is now depending directly on the number of simultaneous calls that we have. So something that is more close to our capacity definition, right? So if we set a maximum value, a minimum value on AB over N0, then, so we say this must be greater or equal a constant, which is AB over N0 minimum, right? Then, of course, we can solve by n and translate this equation into a capacity limitation, right? Simply, right? So we set the minimum threshold, AB over N0 minimum, that's the threshold. This is a constant value, okay? And given this value, we can calculate the maximum number of simultaneous calls that we can put in the system. This is given by 1 plus the processing gain divided by the threshold, okay? Minus something, which is n divided by PR, okay? This value n is the noise power divided by PR, this is the signal power. Typically, this value is small, less than 1, right? So usually we can, approximate the final value, ignoring this last component, neglecting this last component. Okay, so this is n. This is the equivalent of the value that we can easily see in TDMA system. The number of channels that you have, well, this is kind of an equivalent number of channels that you have for having simultaneous calls in TDMA, right? Okay? Let's make some numerical examples in order to better understand, what kind of values we can have, right? So let's take, for example, GP equal to 128. Why this weird number? Well, it's not a weird number, it's a power of 2. And we know that by our examples that typically the spreading factor is obtained with families of orthogonal codes that are power of 2 in length, right? So 128 is actually the spreading factor which is used in UMTS for voice codes, okay? Of course, I'm approximating GP with the spreading factor. It's not completely true, but it's a good approximation, right? Let's assume, for example, that AB over N0 has a minimum value which is 7.5 dB. 7.5 dB is pretty low, right? But it's already, reasonable, right? Then we have another example next to the on the right, which is 5.1 dB, okay, which is even lower, right? So we are considering two examples in which we are considering a quality threshold which is not particularly high, right? Okay. Now, if we consider the first one, which is the more stringent one, and we make calculations, what we get is 23. And if we use the more relaxed threshold, 5.1 dB, what we get is 40. These are corresponding to a bit error rate with a BPSK, QPSK modulation, which is 10 to minus 3 or 10 to minus 2. So already pretty high, okay? But that's, irrelevant at the moment. So my question for you is, 23 or 40, is this a big capacity or a small capacity? With what should I compare it? Sorry?
They are proven by the fact.
Sure, okay. but for the moment we are not considering an area, right? We are I'm trying to, this is the first part, and I'm trying to convince you that capacity is a number of simultaneous calls, right? Simultaneous channels. Later on, we need to change this definition and move to something which is related to an area, right? But for the moment, is the number of simultaneous calls. Is this number small or big?
We have to compare it with the requested services.
With the traffic? Do you want to compare with the traffic? When you have a box, a carton box, right? You have to say, is it big or small, right? If you buy one like this for putting a ring, it's a small one. If you take a one because you are moving, you are moving somewhere else, right? You are changing your apartment, then it's big, right? So the capacity is capacity. Can be big or small, and this is, of course, something that should be related to what you want to put in the capacity, right? But the comparison can be done, for example, with other systems. So if I use the same bandwidth B for a TDMA system, do I get a larger capacity or a smaller capacity? The capacity that I'm getting here is larger or smaller than the one that I would have taken with TDMA, for example?
In TDMA, I think that GP is equal 1. Maybe.
With TDMA, GP is equal 1. That's more or less true.
So it's bigger.
It's bigger here. Do you agree? Do you agree? Really?
It's smaller. Small.
So this is what I'm saying, right? So wait a second, because you answered to my question last time on the equivalence of CDMA and TDMA, right? I'm saying you have your bandwidth B,
1 plus this one.
right? And this is B, and I'm saying how do you compare the capacity in case you use the same bandwidth B for CDMA or TDMA? For simplicity, for example, you can assume that TDMA is an efficiency close to 1, right? You don't have a big guard time because we make all the compensations that we can do, right? So if I make the calculation there, assuming an efficiency of 1 bit per hertz, which is the one that the assumption that we made before, what do I exactly get with TDMA? What number? Can you give me a number?
1 plus.
N, max. Number of simultaneous calls. How many?
The number of slots.
The number of slots. How many slots can you put? 10.
1 plus.
Sorry?
1 plus this one.
1 plus 24, 41, what? What number? Give me a number.
Number.
A number. We have 2 examples. I want a number. It's a numerical example. No, I don't want a formula. I want a number.
Only 1.
Yes.
Only 1.
Only 1.
Yes.
Only 1. Like your colleague. You are teaming, right? Okay. Interesting. Any other number? We can at this point we can even start giving random numbers. Considering that we start from 1 only answer, which is the answer is n equal 1, right? Why don't you try with another one? Anyone? Too shy? Let me put this way. 1 extra point at the exam if you give me the right number and the reasonable explanation why. 1 point. 1 extra point.
Okay.
Yes, try. Yeah, go ahead. Come on. You see?
I would say
2. Interesting. Okay. Okay.
because
Okay, the answer is wrong, but go ahead with the explanation.
I will try anyway.
Try it.
Because the GP is 1 and the SNR EV over N0 doesn't have the interference part. So,
You don't have interference, okay.
but depends on the noise and the power received. So
Okay.
it's not
Anyone else?
SNR minus NDB minus SNR minimum minus the number of the channels. No,
A number.
not the number.
I don't have many
But there is
numbers
no
written on the slide, right?
Yes.
You give up?
No.
No, of course.
You give up? I will take the extra point for me, right? That's surprising, right? Usually I get. So when you have TDMA, right? You use time slots.
Yes.
So basically, you have a periodic. So this is time, right? This is time, and we need to calculate this number. Okay. Point is that we need to calculate it in a way which is coherent with the transmission rate of each of these signals that, of course, we don't know, right? But we know much more than just the rate of the individual signals and the bandwidth B. Because we know GP, which is equal to 128. Since I'm assuming an efficiency in bit per hertz, which is equal to 1, this is also equal to what I call the spreading factor, right? So the spreading factor is the number of cheats per symbol, right? Right? Correct? So our codes here are 120 cheats long, right? So is there a way to make TDMA equivalent to CDMA? Yes. I can use a code which is 1, 0, and 127 zeros. 0, 1, so on, 0, 0, 1, and so on. How many can I make of this? 128, right? Using 1 bit per slot, or any number of bits per slot in TDMA is irrelevant, you know. What is important is the number of time slots in total, right? So, how many time slots do we have? 128, right? So, making the assumption that this system has the same bandwidth, the same rate of each channel, and an efficiency of 1 for TDMA, we could accommodate in the same system 128 simultaneous transmissions. So N23 is very small compared to what you get with TDMA. Clear? Clear for everybody? So the right answer was 128, and the explanation was exactly what we said last time on the equivalence between TDMA and CDMA in some spatial conditions, right?
But Professor,
Aha.
in this case, you didn't consider SNR, the minimum SNR.
I didn't. I agree, but the point is that I don't need to consider, because if I'm guaranteeing that a B over 0 condition is satisfied under this formula, it is for, and in TDMA I don't have interference, I only have n at the denominator, so it is guaranteed for sure, I don't need to do that. I only have the signal power at the numerator and only n at the denominator. Okay, so if I'm in conditions to have this value here, right, which give me 23, then I don't need at all. I don't need at all to make this guarantee. Of course, there is one caveat in which I agree you have a point here. The point is that, of course, you may have, because of noise and because you have a GP which is equal 1 to 238, you may have an area of the cell which is smaller. I agree, right? But also in this case, in practical condition, this does not happen, right? Typically, it's through the opposite. We will see in a moment that with CDMA, you tend to make the areas covered by the cell smaller than in the case of systems with orthogonal. Okay? Clear for everybody? Clear for everybody? So, okay. So this is one example in which you need to don't get lost in the details, which are important, right? All the details that you study in the other courses, right, of communications, for sure, these are important. But at least, some fundamental, reference points must be always there for you in order to understand, how you are playing with the degrees of freedom that you have in any transmission systems, right? Here we are playing with one specific degree of freedom, which is putting all the signals all together in order to make GP high. So GP high, of course, has an advantage, which is not clear at the moment, but I will make it clear in a second. But for sure, does not contribute to the increasing capacity. So you may say, okay, why do they design a mobile system, mobile network based on CDMA, if the capacity that you get is much smaller? The reason is relatively simple, even if questionable in any case, and the reason is that in a mobile radio network, you don't have a single cell. You have multiple cells. And since you have multiple cells, interference does not come only from transmissions in the same cell, but also from transmissions in nearby cells, right? So if you put these together, then sometimes you may conclude that the capacity that you get from the system is good, right? This is a story that is particularly interesting, dates back the end of the 90s, beginning of years 2000, when in particular there was one professor and in an American university and one company founded by the same professor that somehow made the point in the community in order to demonstrate the advantage of using CDMA for these systems. The name of the professor is Viterbi, Andrew Viterbi, and the name of the company, which is still around, is Qualcomm, right? So Viterbi founded Qualcomm, and Qualcomm was the first company that basically made all the basic technology for CDMA, and in particular the patents related to CDMA. That's the reason why still today a chipset for CDMA is more expensive than a chipset for LTE, for 4G, because of the royalties that we pay to Qualcomm, right? So Qualcomm is kind of, Qualcomm not today, maybe Qualcomm 10, 15 years ago was the kind of the dream company, the dream because for a shareholder, right? Because it was a company that most of the revenues were from royalties, right? A dream company because even if you don't work, you get money, right? So that's why it's a dream company, right? You get money even for doing nothing, right? Which is not always completely true, but because it's a dynamic equilibrium, right? Still. Okay, but anyhow, okay, let's try to understand a little bit why, you know, it's not completely nonsense to have CDMA in mobile networks, right? So one of the reasons is, for example, that when you consider noise coming from interference, actually, you in the capacity. So basically, you have in the formula here, you have directly interference impacting directly the maximum capacity, the capacity. Okay. So if you have a way of decreasing interference, you directly gain in capacity, right? Is there a way of reducing interference? Well, of course, there are many ways of reducing interference, and this is the reason why these systems can directly benefit from these. And one of these is, for example, using silence suppression. Silence suppression. What is silence suppression? So, first of all, these kind of considerations have been done for telephone calls, right? So the main service was, and is still today, telephone calls for CDMA, except for the data services that I will explain you later on. They are not exactly based on CDMA. Okay. 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 So you know that we have a challenge out here, right? Which is a lecture on voice coding, right? One of the components of voice coding, of smart voice coding, is silence suppression. So this silence suppression is a way of transmitting coded voice bits only when the speaker is speaking, and not when the speaker is silent, right? Okay, this is an interval where I was not speaking. We should not transmit coded bit for my silence, right? And even in between words, or even between what we call phonema, I don't know exactly the English name, but anyhow, you have small intervals of time between the sounds that make up a word, and these can be micro-silence, that even those can be suppressed. So you have a number of small silences that can be used smartly in the voice coding process, such that you don't generate bits when you have silence, right? That's a way of. So this is also the reason why when you have voice coding and you have silence suppression, we use silence suppressions in mobile radio networks, right? So always, right? When you speak on the mobile phone, and also today even in fixed LAN networks, and you make a call, you usually have silence suppression, right? When you have complete silence, right? What do you usually say, right? We have complete silence. Are you still there, right? Right? And this is, I guess when you speak to the phone to your boyfriend or girlfriend, sometimes, and you are arguing, right? Sometimes you say, okay, are you still there? Are you listening, right? Well, okay, that's not a good thing, right? Because if you see complete silence, that's not comfortable, right? You need to at least say yes, 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 right? Something like that, right? That's typical, right? Well, to avoid this problem, we have what we call comfort noise, right? So in voice coding, we have comfort noise. What is comfort noise? Comfort noise is locally generated noise. So not noise coming from the other side, but it's locally generated. There's a bit of noise that can be you can hear on the speaker in order to make you aware that the conversation is still on, right? That you don't have it, the call didn't drop, right? So you can continue speaking and arguing because on the other side there is someone hopefully listening to you, right? That's what we have, right? So comfort noise. Anyhow, press silence, you gain in capacity. Because basically, at the denominator of our formula, the interference is the average interference. Not completely true because it depends on how many conversations you have, but we can say, okay, if, for example, I have an activity factor of 0.5, which means that I have 50% of time which is silence. Usually it's bidirectional, so that's reasonable, okay? Even less probably than 50%. Usually the number that you take is 40%. That's rule of thumb for the activity factor of voice. Okay? So basically it means that only 40–50% of time you generate interference. Rest of the time you don't generate interference, right? So the denominator must be multiplied by 0.4, 0.5, right? Which means that AB over 0 is double or even more, right? So in terms of capacity, you gain, right? So if we consider in this example the activity factor is the standard activity factor that is considered by for network dimensioning, which is 42%, right? 42% is the right name, right value. Then of course you start getting a capacity which is much higher, 55 in the first example and 95 in the second. It's not 128, but start getting close, right? So, okay, so somehow if you have a system like CDMA, which is converting directly the interference constraints into capacity, and you have good instruments for limiting interference, then you directly gain in capacity, right? If you put things together, for example, in multiple cells, well, you can even make models, much more sophisticated models, that can show you that in some cases you even gain with respect to orthogonal channels. Yes?
I didn't understand a previous thing, when you told about the TDMA problem, about the multiple cells. It's due to the fact that there is a lot of cells, and so there is interference even in TDMA.
Or there is interference or even in TDMA, of course. That's the point. We will come back on this. But if you have multiple cells, then of course you have other cells using the same carriers, the same frequencies, right?
Yes.
So even if in the same cell you have orthogonal channels, you may have interference even in systems like TDMA or FDMA, in the case of LTE or 5G, coming from other cells, right? So you need to deal with this interference, right? So the comparison is TDMA with interference only coming from outside into the cell, and CDMA with interference coming from outside and inside, okay? But, interference coming from different cells, it's there anyhow, right? So that's the point. Clear? Clear for everybody? Now, can we calculate the capacity in the case of multiple cells? Well, the capacity in the case of multiple cells is much more complicated, because the formula in principle is the same, right? The formula in principle is the same. So we can write out the formula like this, right? However, the problem is that when we write the formula, okay, let me explain 1 second. Intra-interference means interference generated inside the same cell. Inter-interference is interference between cells, generated from other cells. Okay, this is at the denominator, right? So in principle, you can generate, you can write down the formulas exactly like before. Unfortunately, at the denominator, you have 2 components. Okay, one component is the one generated inside the cell, and the other one generated outside the cell. Okay, if you assume perfect power control, then for these components, those related to the same cell, you can write as a function of PR like we did before. But we cannot do the same for the interference coming from different cells. Why? Sorry?
Because you cannot know
It's obvious for everybody. It's obvious that we cannot replace this one with PR. Why can't we replace these terms here with PR? Can you give me a simple answer? Sorry?
Different cells.
So?
Different becomes different estimations of.
Different?
Like you don't know what's the power of the other transmitter or receiver being in other cell. You are not in the same cell.
Okay, but I'm receiving some power from them.
But
Why the power I'm receiving from them is different from PR?
Different power control in another cell.
A different. Let's assume that the power control is identical.
different distances. The distance is different.
Of course, right? Just to be sure, everybody, because I usually see some mistakes in the exams of these simple things, right? So you have your base station here, your terminal here, another terminal here, another base station here, right? So I'm controlling the power of this one such that the received power here is here, right? And this is G, right? I'm controlling this power such that the received power here is PR, right? So, but I'm controlling the power here, and I'm getting interference here, right? So I don't know G prime, and I don't know the transmitted power here, which is controlling, right? So of course, here what I get is in general different from here. Clear? Clear? Okay. Good. How much is it? We don't know. It depends on how far they are, how many they are, positions. You know, you have a number of different possible scenarios in which you have different values, right? So can we make an approximation assuming something? Okay, if we want something like before, something which is close to reality, impossible, right? Unless you start making assumptions on the statistical distributions of this stuff. Is it possible? Yes. There is a branch of traffic theory and probability theory, which is known as stochastic geometry, okay, that can give you answers to these questions, right? Very complicated. If you consider traffic theory complicated, I would not recommend you to consider stochastic geometry, right? Very, very fascinating, you know, area, but you know. Can we make a very rough approximation? Well, we can do what Professor Videbi did when he wrote his first paper on this, which is, okay, let's assume that the intercell interference is proportional to the intracell interference under homogeneous traffic conditions, right? So which means that the component is equal to the intracell components times a constant f. This f, of course, depends on the scenario, how close the cells are on average, and so on. You can say, okay, let me tune f depending on the specific layout of my system, right? Usually, this is something that is highly questionable. Usually, the values that were recommended at that time for the calculation of the capacity were between 0.4 and 0.6. Okay? Again, this is not completely true. If you are in a dense urban area, typically F is much larger. Okay? Just to clarify. But okay, let's keep the values that were suggested by Viterbi, and let's assume, for example, 0.5, and of course we can go back to values that are different. There is a mistake here, of course, because this example does not include that one, but of course we get some capacity values that are in the order of 20 something and 40 something in these two examples. So you make the calculation, right? Now the point is that we have, let's see, 25 or order of 20 something maximum conversations per cell, right? Now we have to compare these 25 with what? With what we have in TDMA in a multi-cell scenario. Calculating the capacity of TDMA in a multi-cell scenario is non-trivial. It's not like before when I asked you the question. You need to understand how to distribute the available carriers, the available channels between different cells in a TDMA system. In case of CDMA, you don't have even a problem. You just use the same spectrum for all, period. In the case of TDMA, this is not true. You make what is called a frequency plan or frequency reuse plan, right? So we will come back to this problem of frequency reuse in TDMA systems in order to understand what can we really do in order to calculate the capacity per cell in a TDMA system, right? And also understand why today with OFDMA we don't have a frequency reuse like we usually have with traditional TDMA systems, mainly for reasons that are related to the use of directive antenna arrays. Okay, so we have to come back to this. But before moving, just one simple note on this. I just used so far the example of uplink, right? Is there a difference in the case of the downlink? Well, of course, there is a difference in terms of the downlink. In terms of the downlink, if we are in a single cell, isolated single cell, okay, in the downlink, is there any difference between TDMA and CDMA? Well, you should say TDM and CDM. No, because in the downlink we can use orthogonal codes. So somehow it's time division or code division are equivalent, perfectly equivalent, right? We don't have interference because we can use orthogonal codes. Okay? So the only difference comes from the multi-cell scenario. In the case of multi-cell scenario, of course, even in the downlink of CDMA, we have interference exactly like in TDMA because we have interference coming from the other cells, right, in the downlink. Actually, there is one small point which we need to consider, which is the following. If you have multipath propagation, we know that in addition to the fading effect that you have because of multipath, you also have delay spread. So delay spread because of the different distances that are traveled by the different signals, right, in multipath. If you have delay spread, unfortunately, this has an impact in CDMA because you lose the orthogonality property because you have, of course, some uncertainty in time. If you have some uncertainty in time due to the dispersion in time of the different signals that combine to the receiver, then you may lose some of the orthogonality property. For this reason, the intracell interference in the downlink is usually non-zero, but can be a value which is non-zero and depends on the propagation environment. So if you are in an environment where multipath has an effect as a big delay dispersion, then of course you have a rather big intracell interference. If you are in an environment with a limited time dispersion, then you typically have a very limited intracell interference or zero intracell interference. So typically you can write down a formula where you have alpha interference times interference coming from the same cell, intracell interference. Alpha can be zero in case you have perfect orthogonality, or can be something that can go up to 1 in the case in the end you don't have actually any orthogonality. Okay? Of course, again, same assumptions like before. If alpha is close to 0, you basically see that the value that you get from the formula is usually higher than the uplink. And this is the reason why these systems are limited in capacity usually by the uplink and not by the downlink. Okay? So if you have symmetric traffic, like in the case of voice calls, then and you write down the equations for the capacity in uplink and downlink, then the one limiting will be the uplink and not the downlink, right? Simply because usually intracell interference is 0 or much lower than in the uplink. Of course, in the case of non-symmetric traffic, like for the case of data connectivity, data connections, this is not always true because usually data traffic is asymmetric and you have more traffic in the downlink than in the uplink. Okay, so I just already said to you that you have a spreading factor, which is something that you can use for approximating the processing gate, right? And that's the main reason why you get that. Very well. Let me go fast here in the power control. I already mentioned power control. I just want to make a point here, which is something that is relevant for understanding the difference between the simple power control that we call open loop and the more sophisticated power control that we use in the G2G systems, which is the closed loop, right? So somehow the mechanism of the closed loop power control is based on the estimation of the signal to interference and noise ratio at the receiver. And the goal is to make this value constant at the receiver. Not the receiver's power, but the signal to interference and noise ratio. Clear? Okay, that's the point. So I said to you that in the case of the isolated cell, this is equivalent to the open loop. So nothing changes, really, right? Why do we have a difference in the case of multi-cell scenario and how we can really manage it? Okay, that's my point. Okay. So the point is the following: if you have a B over N0, you basically can write the formula like before, with the received power divided by the total interference intracell, intercell plus noise. Okay? Very well. Now, if you want to use an open loop power controller, you just make GI, PI constant. But if you use signal to interference and noise ratio as your target, so you want to make this value, which is, I mean, you can multiply by GP, but that's a constant, that's irrelevant. So you want to have this ratio constant, so signal to interference and noise ratio, or if you prefer, AB over NL0, this value constant, basically you are writing down a condition, everything greater than or equal to a value, which is an equation that puts together all your variables. What are your variables? Your variables are transmitted powers, PI, right? So I want to set the transmitted power for each terminal, right? So if I write that equation and set it equal to a constant, I'm writing an equation that includes all variables. If I just write GI, PI equal to a constant, I only have one variable per equation, right? And I can easily calculate the value of PI to get the constant, right? That's easy. Clear? If I write that equation, I have all variables in that equation. And if I want to set all these variables, I need to write a number of equations, independent equations that are exactly equal to the number of variables. Actually, this is the number of equations that we have because we have to ensure that that value is equal to a constant for all signals at the receiver. So for signal I, signal J, and so on. So we can write down a number of equations which is exactly equal to the number of variables. So we can, first of all, we can linearize the equations, right? And what we get is a system of linear equations with n variables and n equations, where n is the number of interfering signals. Clear? So this is in mathematical terms, this is the difference between the open loop and closed loop. So this makes a big difference, right? Now, clear for everybody? Clear for everybody? Okay? So it means that if I give you the value of the attenuations, not only the attenuations between transmitter and its own base stations, but all, the full matrix, right? Also the gains, the cross gain between terminals associated to other base stations, all coefficients. So you have two indexes there. Okay? You have two indexes there, I and in that case BI, which is the index corresponding to the base station to which terminal I is assigned. Okay? So if I have a complete matrix of coefficients G, then I can write down the equations and solve the system of linear equations. Okay? Clear? Very good. The point is, how many situations can we have, right? So basically we can have three conditions. In the first condition, the solution of the system does exist, and it's compatible with the powers that are available at the transmitters. At the transmitter, you cannot transmit infinite power, of course, but you have a power limitation. So I can calculate the solution of the system and check if the values of the variables pi are all within the thresholds, the maximum power, right? If this is the case, then I have a solution of the system which is a stable solution, and this is something that can be proven. In case of the open loop, the closed loop power control, the one that is based on transmitters that adjust power based on the feedback from the receiver up and down, so it's a closed loop control, we can also prove that if the solution exists and is like this, so stays within the thresholds, then this closed loop control will converge to this equilibrium point. So the solution of the system is the equilibrium point of the closed loop power control, where you have a loop for each transmitter and receiver. Okay? First, this is the best case, of course. The solution exists and we converge to that solution. The second possibility is that the solution exists, but unfortunately, one or more of the powers that are provided by the solutions are too high for the transmitters. So we need more power, In that case, the system somehow is above the capacity, right? Because we cannot guarantee a good quality for all receivers. Which means that at the receivers, at some of the receivers, the quality that we get is below the signal to interference and noise ratio, or a V/N0, that is our quality target, the constant that we have used. Instead of getting, 10 dB, we get 5 dB. The quality is not what we expect. And if it is too bad, we drop the quality. Okay? So somehow we are above the capacity. Third possibility is that the solution doesn't exist. Okay? So in the case the solution doesn't exist, we are also above the capacity of the system. we have too many signals, and there is no point that can guarantee that all of them can get the target value. The solution doesn't exist. In that case, unfortunately, the closed loop power control will start getting unstable. Why unstable? Because basically the mechanism is this. If the target quality is not met, increase power, right? Since the solution doesn't exist, everybody will start getting increasing power, step by step. So everybody will start increasing power until the maximum one, right? So it's kind of an explosion, right? Everybody will start increasing the power until they get the maximum. Once you reach the maximum, the quality is not good, you start dropping codes, right? So the system will go back to some stable condition, but passing through a condition which is unstable, right? So of course, we need to avoid these conditions. So, in the first case, we say that the system is stable, okay? And we are within the capacity limits. In the second case, basically we could be stable, but we don't have enough power. What does it mean we don't have enough power in practice in a mobile radio network? Don't have enough power means that we are, for example, too far from the base station, right? So we say that the cell in that case is noise limited. Noise means that, of course, we don't have enough power, so somehow we cannot get to the solution, right? This condition is typical of large cells in areas of low density population. The third case is when you are above the capacity, period. Nothing to do with noise and available power, right? So which means that you have a system, you start adding a call, you get a new equilibrium point, then you add another one, you get another equilibrium point, and you, in particular, if you are, for example, in small cells in a city center, right, and you are very close to a base station, you use very little power, right? So your solution makes you use very little power, okay? So you add another one, of course you increase a little bit the power, right? But you are still stable. At a given point, you reach the maximum value. You exceed the Nmax that you can tolerate with your system. From that moment on, there is no solution at all. So everybody will start increasing the power. So until the point where just one step before you get into the unstable region, so until you are at the limit of the capacity, everything is stable and with low power, right? But if you exceed the capacity, then everything will explode somehow, okay? So that's why you need to guarantee in this system that you always stay within the capacity, right? And this is the reason why in CDMA systems you have a strict control of the simultaneous numbers of calls that you have, right? Controlling this is fundamental. And how this is done, there are many different ways of doing this. And the mechanism in general that you use is known as call admission control, right? Ideally, what you can do is to use power control as a benchmark. For example, ideally you can say, okay, let me try to see if I can make another, if I can put another call. So you add a call and you check if everything is stable. If it is not stable, you will reject the call. So it's kind of a trial period, right? Ideally. This is something that could be done. Otherwise, you have to use other mechanisms. Let me just mention one important thing that is, no, I don't have time. next time I will make this point and clarify what's the difference with respect to